Okay, so again, what we did is we've been talking a lot about different parts of polynomials. Just want to kind of to review that and kind of look at how we can use, it might help you to do like a step-by-step process or have kind of a flow chart to help you graph a polynomial function. And if we're practicing today, I would recommend too, you graph I noticed some students will like go through and do all the end behaviors. And they'll go through and do all the y-inters. It's kind of nice to do all for one problem, get your 4 pieces there, then get it on the graph, make sure it's right, then go to the next one. Because that's more like a test, you know, to kind of practice like the game time. But so the first thing we do when we see a polynomial is we just want to identify what the end behavior is. Now, you can write your 2 little statements if you want. It's fine. A lot of times I'll just make myself a little note. If the instructions are to graph the polynomial, and it doesn't say give the end behavior using limits, but I might say, well, if it was that one, I would just put like a little thing like that. Okay, both ends are up. Or if it's a cubic polynomial with a negative leading coefficient, I might write a little picture like that to remind me that I'm going to be up high to the left and down to the right. It doesn't have to be a formal statement, but you want to think about what's the end behavior going to be. Next thing, a super easy point, you might put it on your graph, you might just label it later, is the y-intercept. Okay, now if your polynomial is in standard form, right, where it's all expanded, the y-intercept is always the constant. Easy enough. If it's in that factored form, like you give it with a bunch of factors, all you do is you just plug in a 0 for every x and solve for the output. Any function ever, that's how you find the y-intercept. It's always just put in zeros. When it's in standard form, all the x's become zeros, and that's why you have the constant. If it's not factored, you'll need to factor it completely. It's step 3 before you do step 4, which is to set each factor equal to 0 to find your x-intercepts. Okay, now, for right now, they're all going to have solutions, but sometimes in the future, we'll see where you might have a like a complex or number, you know, with an I in it. Well, those don't give you x-intercepts. Those don't really mean anything in terms of the graph. Right? They mean something in terms of the polynomial, but not the graph itself. And then once you do that, if any factor is raised to a power, then find the multiplicity of the x-intercept. And when I mean raised to a power, it should be, you know, if you have the factor x minus c and it's raised to the 3rd power, that would be a multiplicity of 3, right? Now, if you have something maybe later on, maybe you factor and you get x squared plus 2, and you're like, I can't factor that anymore, right? And then you try to solve it and you get complex numbers. This does not have a multiplicity. That's just not going to give you x-intercepts. So it's got to be the parenthesis, and the power on the outside of the parenthesis indicates a multiplicity. Okay, so we can look at that on one of these. So for an example, just on the paper I just gave you, this graphing polynomials continued. Let's just try to run through this process and see how we can do this. Okay, so we have, let's try the second one here. It was g of x equals x to the 4th plus x cubed minus 12x squared. Okay? So we have a polynomial. This is in standard form. So let's kind of run through our steps here. And this, again, this is the second one on your paper. So the first thing I'm going to do is just think about my end behavior. Okay, so this is a 4th degree polynomial. It depends, some of you remember the pictures, some might remember the formulas. How I usually think of it is the leading coefficient, and I usually think of it in terms of moving my arms up and down. But I know the leading coefficient is positive, so that right side's going to be up, right? I know it's an even degree, so that means both sides are going to be up. So for my end behavior, it's going to look something like that, right? It's going to go from the top left, do some stuff, and go back to the top right. Again, if you wanted to write it out, you could write it out. But for here, it didn't really ask us to, so that's okay. Oh, it does say state the end behavior, so I guess we got to do that. So as limit as x approaches infinity of g of x is infinity, and the limit of g of x as x approaches negative infinity is infinity also, right? Both sides are up. So I did end up right. The next thing is the y-intercept. Well, in this case, it's expanded. Is there a constant term? There's not, right? If I put 0 in for x, I get 0. So that would be that. And then we need to factor it. So always fun with factoring. First thing we do is we take out the greatest common factor, which would be x squared. I wanted to do this one in particular because people tend to forget that x squared also provides x-intercepts. That's a big problem, or a big tripping point. So we get x plus 4, x minus 3. I'm going to push this over here. Okay, so we have that. So then this tells us there's 3 factors here, correct? We have a factor of x, we have a factor of x plus 4, and we have a factor of x minus 3. So with that, maybe it's helpful here, make a little table. For the factor x squared, that's going to give us an x-intercept at 0, 0, correct? Now the factor was squared, so that means we have a multiplicity of 2. Which, it's really important to spot the even multiplicities because that's where it bounces, right? If you miss an odd one, your graph will be a little bit wrong, but you'll still be able to get the shape to work. You just missed that little cubic piece, right? Where if you miss a bounce, you're just on the wrong side of the x-axis. You can't get back across. So x plus 4 gives us an x-intercept of negative 4, 0. And then x minus 3 gives us an x-intercept of 3, 0. Now again, I don't necessarily write all this out for every problem, but hopefully, you know, that helps you there to see that. You have grids on your paper. If you decide you want to use a straight edge and just blank paper to graph like I do on the board, that's completely fine. There's rulers and straight edges in the back. I think those little grids can get kind of cluttered. So if you just have an axis, because really we're just trying to show significant points here. So 1, 2, 3, 4. So negative 4, 0, 3, 0, and 0, 0. And I would recommend too, make your x-intercepts nice and big. Like, we got to make sure we hit them. You don't want to lose one, right? So now with this, we know there's a multiplicity of 2 at this x-intercept. So it's either going to come down and hit this one and go back up, or come up and hit it and go back down. Okay, but with all this information, we don't need to make a sign table because we have enough information. End behavior tells us that we start up here, correct? This 0 is just a typical 0, and that typical x-intercept, right? It just passes straight through. So we're going to pass straight through. We said here we're going to bounce, correct? Because it has a multiplicity of 2, back down, and then back up. So it's going to look kind of like a W, I guess. Fat dot theorem, make sure it hits the point, and there we go. Now, if you notice when I sketch these, and this is why this way is kind of an advantage over the grids, there's no scale on the y-axis. I don't know how low this goes. I don't know if this is exactly the shape, but as a grader of something like this, the things I would look for is, do they exhibit the proper end behavior? Do you have the proper x-intercepts? Is it above the x-axis when it should be? Is it below the x-axis when it should be? It should be smooth. Like, I mean, it might look kind of, I mean, sometimes it's hard to get them right, but try not to make them look like a sawtooth, right? They should be smooth and continuous. There should be no sharp edges. Safe for children. So that is kind of an example of using that 4-step process. Okay, so hopefully we tried some in the standard form, but let's look at one here in factored form, which it get harder because you're going to get more multiplicities because you don't have to factor it, so they can give you kind of ugly looking things like this. But, and a little bit tougher to find like the y-intercept and maybe the end behavior, but you get to skip factoring. So I think it's a win, like, you know, because factoring is usually, well, we'll spend the next week or so looking at different ways to factor because it's kind of, there's a lot we can do with that. So if I look at this one, if we kind of run through our things before, like we did before, to find the end behavior, okay, we'll just really analyze this function, right? We want to talk about all these pieces, put it together on a graph. So for the end behavior, you really need it in standard form so you know what the leading coefficient and the degree are. You need to know what that leading term is. The nice thing is that with these, we can imagine that we're expanding this out. We don't want to expand it. It would be a 6-degree polynomial. It would be like 10 minutes of your life you'd never get back. We don't want to do that. But we do know that if we take this thing and cube it, the biggest degree x in there is going to be an x cubed, right? And then here, when you square it, you're going to have an x squared. And then here, when you do this, you have an x. So the biggest term is going to be your x cubed times your x squared times your x. So we know that the leading term is going to be x squared, or I'm sorry, x to the 6th, right? It's 3 plus 2 plus 1, add them up, you get 6. Just so if we multiply that all the way out, you're going to get an x to the 6th in front. I have no idea what you're going to get after that. That seems like way too much work, right? I don't want to expand it. But that does tell us that this is an even degree, and the leading coefficient is greater than 0. So in terms of our limit statement, as the limit as x approaches infinity of p of x, this always, if the leading coefficient, in this case the 1, in front of the x to the 6th is positive, as you go to the right, it will be positive. Which makes sense, right? Because if x is going to be a positive number, so whatever power you take it to is going to be positive. And then if you multiply it by a positive, it stays positive, right? And then we'd also have that the limit as x approaches negative infinity of p of x. It's an even degree, so we know both sides are the same. Right? So we're looking at a U-shaped graph. Okay? It's not going to look like this. There's going to be a lot of weird behavior near the x-intercepts, but overall, the ends are going to go up to infinity, to the left and to the right. For the y-intercept, I didn't mention this before, but especially when you're graphing on the grids like you have on your worksheet, that's another reason they're really not that good. I'll try putting lines on stuff like I use, but you don't always have to label this on your graph, but you do always want to know how to find it. Right? So in this case, it's a little bit harder to find. We don't have it all expanded out, but we could go ahead and take the function we do have. We can replace every x with 0, and then we just have to multiply it out. Right, so p of 0, just a little function notation. 1 cubed is 1. Negative 3 squared is 9. And then times negative 7. So I guess that's negative 63. Right now, p of 0 is negative 63. Or you could write, I like to still maybe write it as a point. It just seems, when I see this, I definitely think it's a point. This, I think, what am I looking at for a second? Okay, so there's that. Now, in order to factor completely, we get to skip step 3, which is great. Now, each of these factors is going to provide an x-intercept, right? But we see that like this factor is cubed, right? So this, the associated x-intercept, well, here we can just write this out and see it. So for the x-intercepts, so if the factor x plus 1 cubed gives you an x-intercept of negative 1, 0, right? But it's going to be a multiplicity of 3, which means it's going to either, it's going to look like a cubic as it goes through there. 3 is cubic, looks like a cubic. And then we have x minus 3 squared, which will give us the x-intercept 3, 0. And that has a multiplicity of 2, which means we're going to have a bounce. And then we have x minus 7, which gives us 7, 0. It has no multiplicity. It's just going to be like a typical. So look, if it's multiplicity of 3, it looks like a cubic, right? If it's multiplicity of 2, it'll look like a parabola. multiplicity of 1, or you don't say that. If it has no multiplicity, it just looks like a line when it passes through. So let's try to put those onto a graph here, or just a sketch. I think sketch is probably a better name because we don't plot any points, right? Like we don't have to make a table and plug stuff in. So we get -1, 0, 3, 0, 7, 0. Our end behavior, remember, as we go to the left, it's gonna go up, correct? So when I graph, I just usually graph left to right. I'm gonna start up here, gonna come hit this first x-intercept, which that's where there was a multiplicity of 3. So it's gonna come down here and go through, but it's gonna have a little point of inflection. And I kind of like to map it out in my head before I start drawing, get a smoother curve that way. And then it's going to come back up, and it has to hit this point, which has a multiplicity of 2, which tells me it'll come up and it'll bounce. Then it keeps going to the right, and then it's going to hit at 7, but 7 does not have a multiplicity, so it'll pass straight through. So now if I look, I started up high, and I'm going to end up high. Is that what I wanted? Okay, if you ever find like that you ended down here, and it doesn't agree with the end behavior, it means that either you missed an x-intercept, or you missed a multiplicity, or whatever. Right, and all the multiplicities it's like saying this is an x-intercept like 3 times. But obviously you can't put 3 points on top of each other and tell, but it does have an effect on the curve. So what did I say? So come down. Looks like that. Now, again, you kind of can see there's a point of inflection here. Notice it's concave up and it switches to concave down, is what's going on there, kind of like a cubic. Here we see the bounce. There we pass through. Again, there's no scale on the y-axis. If you wanted to be, you could just add a -63 there, like if you wanted to. That's all you'd have to do, if you wanted to. But that's basically what that graph should look like. Now, I would check it on your calculator. It's even a better check than a key, right? I mean, just see what it looks like. But like when you graph this, it's probably just going to look like a couple vertical lines because it's going to be, your scale is going to be so off, right? But it's good practice probably getting the window adjusted correctly to match your graph if you need help on the calculator. So